Good morning friends. Welcome to Parnika's Tutorials YouTube channel. In this video, I want to discuss about red-black trees. Lot of students face difficulty to understand the red-black trees concept. So I request everyone to watch the complete video for better understanding. First let me define what is a red-black tree and then I will discuss how it is different from binary search tree and AVL tree. Then I will discuss what are the rules every red-black tree should follow. First, let me define what is a red-black tree. Red-black tree should also satisfy the properties of binary search tree and then it is a self-balancing, same as AVL tree. It is also a self-balancing binary search tree. Now, we will discuss what is a binary search tree. A binary search tree should satisfy the properties of binary tree. First, if it want to be a binary search tree, first it should be a binary tree. What is the property of a binary tree? Every node can have at most 2 children. If every node have at most 2 children, then such tree I will call it as a binary tree. Once I got it as a binary tree, then what is a binary search tree? The binary search tree, every node, let's take that this node has a value called 20. Now this node will have the left subtree and it will have the right subtree. The nodes which are there in the left subtree should have the values less than 20 and the nodes which are there in the right subtree should have the values greater than 20. Is it clear? So if it is satisfying this property, then such binary tree I will call it as binary search tree. Now even we have discussed about the self-balancing in the AVL tree. Why should we have the self-balancing nature? Suppose coming to the binary search tree, what is the problem with the binary search tree? The problem with the binary search tree, if it is a left skewed binary search tree or it is a right skewed binary search tree, it is possible. Am I right or wrong? If all the elements which are there in the left subtree are less than the root node, suppose let's take that you have a 6 here and you have a 5, you have a 4, 3. This is possible in the left skewed binary search tree. Suppose you have the elements like 6, 7, 8, 9, then you will get a right skewed binary search tree. Suppose let's take that I want to search whether 3 is there in this left skewed binary search tree or not, then I will take a time complexity of order of n. This is the limitation of the binary search tree. To avoid these limitations, we have went for the AVL tree. What is the AVL tree? We have kept a restriction on the balancing factor. The balancing factor of an AVL tree should be either -1 or 0 or 1. Why we have kept the restriction? To reduce the skewness. If we reduce the skewness nature, then we can restrict the time complexity. So the AVL tree will take a time complexity of order of log n, whereas the binary search tree in a worst case will take order of n. Okay, now you can ask me, sir, what is the difference between AVL tree and a red-black tree? Now AVL tree is also satisfy the properties of binary search tree and AVL tree is also self-balancing one. And coming to the red-black tree, the red-black tree, every node in the red-black tree should have a color consists of either red or black. This is the difference between the red-black tree and the AVL tree. In AVL tree, the nodes will not have any color, but coming to the red-black tree, every node has a color either red or black. We will have a 1-bit value. It represents either it is a red color or a black color. Now let me discuss what is the drawback of the AVL tree and how the drawback is overcome in the red-black tree I will discuss. Now what is the drawback in the AVL tree is when we are inserting the data or when we are deleting the data from the AVL tree, inserting any element in the AVL tree or deleting any element in the AVL tree will create lot of rotations. Already we have discussed several examples. We have LL rotation, LR rotation, RL rotation, RR rotations. These rotations will increase the complexity of creating the inserting and deleting the elements from the AVL tree. Now, this limitation is overcome in the red-black tree. Is it clear? Are you able to understand? This is the limitation in the AVL tree because the red-black tree and AVL tree takes the same time complexity. Even for searching or inserting any element, AVL tree will takes the order of log n, and even red-black tree takes the order of log n. But what is the difference between AVL tree and red-black tree is, in AVL tree, if you want to insert any element or if you want to delete any element, it takes lot of rotations. Those rotations have been reduced in the red-black tree. So I hope you have understood the introduction of the red-black tree. Now let me discuss about what are the rules every red-black tree should follow. First thing is that every node has a color either red or black. That's why it is called as red-black tree. The root node is always black. It is not black, it is black. Every root node is always black. Suppose if you have a red-black tree, suppose let's take that you have like this. Okay, the node which is a root node should be a black color. Is it clear? Are you able to understand it or not? Now this one can be a red and this one can be a red. That we will discuss later. But the first thing is that the root node is always black in color. There are no two adjacent red colors. Meaning is that, suppose let's take that you have a parent. Let's take that you have like this. This is the root node which is black color, and you have a child which is, let's take that red color, and this is also red color. Just giving an example. Now if you want to insert some more element here, then if it is red color, that is what they are saying, there are no two adjacent red colors. Suppose if parent is red color, child should not have the red color because these two are adjacent. Don't think that these two are adjacent. These two are siblings. Are you able to understand it or not? Whereas this one and this one are adjacent, so they should not have the red color. Is it clear that there are no two adjacent red nodes? Now every path from a node including root, this is very important property. Every path from a node including root to any of its descendant null node has the same number of black nodes. Now firstly let me discuss what is the descendant null node. Is it clear? Suppose let's take that you have a red-black tree consists of, this is a black and this is red, this is also a red node. Suppose let's take that this value is some 9. Okay, because it should satisfy the binary search tree, then I have to give some values. Suppose this is 9, let's take that this is some 6 and this is some 12. Okay, now let's take that you have inserted some black node here, just giving an example. Okay, and it is having some 15. Okay, are you able to understand? Suppose let's take that this is also another black node whose value is some 5. Let's take that. Now you have a leaf node. That is one more important point. Every leaf node which is null should be with a color represented black. Suppose let's take that 9 is there, it is having its two children which are in red color. Now 6 have only one child which is a left child. Now right child which is a null. Am I right or wrong? This right child which is null should be represented with a color called black. Suppose let's take that here also you does not have any left child for this 12. Even this one is, we'll call it as a null node which should be represented with a color called black. Suppose let's take that even this node does not have left child and right child. So these also should be represented with a black color. These are null nodes. But usually we will not represent, but these null nodes will be useful for us whenever we are performing insertion and deletion in the red-black tree. So even let's take this one. It does not have the left child and right child. So we can consider them as null nodes with a color called black. Are you able to understand it or not? Now let me discuss this fourth point with an example. This is a root node and you have a nodes black. This is also nodes black. This is also two childs which is in with the color black. Now let's take that some values. Some 15 I am taking. The values here is less than 14. Here you have, okay, let me take 13 here, okay. And here I am taking 14 and here I am taking 12 value. And now let's take that it is 20, this is 25 and this is greater than 15 and less than 20, so I can take some value 19 because the red black tree should satisfy the binary search tree property. So if you look at it is satisfying the binary search tree properties. Now each node I have represented with a black color. Okay, are you able to understand? It is not compulsory that all the nodes will have the red color, but all the nodes can be a black color because the root node must be black, and there is no point that at least you should have one red color. This is also a one red black tree. Now we will discuss about the fourth point. Now what they are saying, to any of its descendant null. Suppose let's take that here you will have a null node. Am I right? Because it does not have a left child and right child, so you will have a null node which is in the black color. Similarly, here also you will have a null node, here also you will have a null node, here also you will have two null nodes, and here also you will have two null nodes. What is this point is that every path from a node including root, okay, from the root, including the root, what are the possible paths are there? Suppose let's take that you can, from this root node, you can go to this descendant null node or this one or this one or this one or this one, any of this one you can go. Now if you take any of this path, suppose let's take that if I want to go here, I will go like this. If I want to go to this node, I will go like this. If I want to go to this node, I will go this way. Am I right? Whatever the path you are taking from every node, including the root, to any of its descendant null should have the same number of black nodes. Let me erase this one so that you will understand in a better way. Okay, these lines. Okay, this is black in color, this is in black in color. Okay, now if you look at it, how many black nodes are there? From here to here, if I want to go, don't consider this one because it is always black. Now 1, 2, 3 is there. So if I want to go to this one, I am taking 3 black nodes from the root node. Suppose if I want to go here, 1, 2, 3, 3 black nodes. Suppose if I want to go here, 1, 2, 3, 3 black nodes are there. 3 black nodes. So if from, this is very important, from every path from a node including root to any of its descendant null node has the same number of black nodes. Suppose let me give an alternative example for it. Suppose let's take that you have a black node which is a root node. Here also you have a black, here also you have a black, black and black. Here you have a red node, here you have a black node. Let's see each property. Every node has either color red or black. Each one I have represented with a red color or black color. The root node is always black. There are no two adjacent red nodes. If you look at only one red node is there, so there are no two adjacent red nodes. Now we need to look at the fourth property. What is the fourth property? Every path from a node including root to any of its descendant null node has the same number of black nodes. Now suppose if I want to go to this null black node, here you will have, already we have discussed, here we will have two null nodes which are represented with a black color. Now if I want to go here, now how many black nodes I am visiting? 3. Here also 3. 1, 2, 3. Here if you have any 1, you will visit 3 because 1, 2, 3. And to this right also you will have 3. But if you come to this one, if you have any null node, because it will also have a null nodes which are in the black color. Am I right or wrong? Because it does not have a left child or a right child. Now if you look at it, this one having how many black nodes? 1, 2. 2 black nodes are only there. But here you have 3. From this path you have 3. in this path you have 2, in this path you have a 3. Now if you look at it, each path will not have the same number of black nodes, then I can call this one as a not a red black tree. So I hope you are understand about the red black tree. First it should be a binary search tree, then every node should have either a red color or black color, then root node is always black color, there are no two adjacent red nodes, and this fourth one also should satisfy. So if someone gives you a tree and if they ask whether it is a red black tree or not, it should satisfy all these 4 rules. If it is satisfying, then I will call it as a red black tree, otherwise I will call it as a not a red black tree. So with this video, I hope you have understood the introduction about the red black tree. If you still have any doubts related to this concept, feel free to ask me in the comment section. In the next video, I will discuss about how to insert elements in the red black tree. Thank you for watching the complete video. Have a nice day.